Hey everyone, Michael Unger here for the MacMillan Space Center. Once again, here for another edition of Ask an Astronomer. I am here, as you can see, in our observatory on a very sunny day on the unceded territory of the Musqueam, Squamish, and the Tsleil-Waututh. It is JWST week. It's JWST, the James Webb Space Telescope, all week. Perhaps you have seen those pictures that have come. Locus for the majority of this episode on those images. Our regular astronomer Marley is on vacation, but we are very honored and excited to have the outreach scientist for the James Webb Space Telescope in collaboration with the Canadian Space Agency, coming to us from the left coast, from Montreal. That is Nathalie Ouellette. Hi, Nathalie. How are you?
Good. How's it going, Michael?
I am doing very well. You must have had a very busy day on Tuesday. We had a small gathering here at the Space Center. And for anyone out there that did watch the live feed, you should have been watching Nathalie and her colleagues give a description of the exoplanet picture, but things just didn't go as planned, did they?
No, they didn't. It's my understanding that I was on the feed for a few seconds. So I did make my NASA debut, my live debut, but unfortunately the feed was dropped. It's a huge machine, these like shows. So they had to keep it moving. They couldn't come back to us, unfortunately. But we did record our presentation and it is available on all of CSA's social media. So I encourage you to go watch it. I think we convey our excitement for the discovery, and it's nice to hear the Canadians describe it too.
Well, exactly. And just to give context to how high the stakes were, especially for me as someone who has been watching NASA, has been hotly anticipating JWST to come out, and the Canadian Space Agency's involvement, this really is the Canadian Space Agency and for Canada as a whole, their biggest moment. This was not only a big moment for you to shine, but for all of Canada to shine as well on the live feed that NASA was putting out, because it's a collaboration with the European Space Agency as well. It was kind of ironic. What I also found kind of ironic is that, we're getting all these images from millions of miles away. We couldn't get an internet feed from Montreal. Come on, what's going on here?
Yeah, no, I totally agree. But even though there was a little glitch there, the collaboration is still at the heart of the success of this project. And I think that we're going to continue collaborating, and hopefully we'll have lots of cool projects to do in the future with NASA and ESA.
All right. Well, since the sun is peeking into the observatory here, and I'm almost being washed out here. Speaking of stars, we got lots of amazing pictures to talk about that the James Webb Space Telescope has just released. So, Nathalie, why don't you take us into this telescope? It is the biggest, most expensive telescope that humanity has ever built. Tell us about the James Webb Space Telescope, and if you're here in YouTube and you're watching, you have any questions about the JWST, or if you're here and you have a specific question not related, Nathalie can probably answer that as well. If you're watching on Telus Optic, you can come on in and join us in the future for an episode. But Nathalie, kick it off with James Webb.
Yeah, definitely. So for those of you who are less familiar with the mission, I'm going to go through some of the really big important points, its scientific goals, and what makes it really different, like a huge revolution in space astronomy. So this is it, the Space Telescope, the James Webb Space Telescope, a very distinctive looking telescope, as you can see. If you have telescopes at home, or if you're familiar with the Hubble Space Telescope, for example, they don't look like this. And it's great, it's iconic, very marketable, but there are scientific reasons why we built it this way. So this is a collaboration led by NASA, but with very important contributions from the European Space Agency, a longstanding partner of NASA. They collaborated on Hubble, for example, but also the Canadian Space Agency, which I work with. And this is really exciting. We weren't part of Hubble formally, but we are now a formal part of the Webb collaboration. We've been working with them for decades on this, and we're going to continue getting great science on this telescope. So I'm the outreach scientist for Canada for this telescope. What does that mean? People might not be very familiar with this term. The name is great in English. In French, my name is so long. It's scientifique chargé des communications sur le télescope Webb. French, wow, like it's so long. But it basically, I do what it says on the can. I am the scientist on the scientific team in Canada who is in charge of doing outreach communications. I'm sort of like the spokesperson for the scientific team. I make sure that all of the science we do goes out into the public, benefits the betterment of knowledge, of understanding our universe. And I do lots of interviews, lots of online content. And yeah, so there's a picture of me visiting the telescope while it was still on Earth, because it is no longer on Earth, it is in space. This is a good picture that shows my dedication to the mission, but this is an even better picture that shows my dedication to the mission. You can see me. Yeah, go ahead.
Yeah, no, definitely describe what you're going on here. But I think that this would be a great opportunity because often we get, and I actually got this question specifically from a child recently, what do I have to do to become like an astronomer or a scientist? Like, what did you do to get the honor of being the outreach scientist for Canada? What was some of the education that led you here?
So I took a pretty sort of typical classical path to becoming an astronomer, an astrophysicist. In Canada, there are very few astronomy departments in universities. Our universities are typically just too small. So I got a physics degree, undergraduate degree at McGill University. And that is really fantastic. That's great. We are physicists. We just do study the physics of what is in space. That's the only difference, essentially. So having a good background in mechanics and quantum physics and nuclear physics, very, very helpful. But after that, I then went on to get a master's degree and a PhD at Queen's University in Kingston, Ontario. But all throughout my academic career, I realized I really loved teaching, as well as all the learning and research I was doing on a daily basis. So I've been involved in science communication for about 13 years now. I was in charge of the on-campus observatory during my master's and PhD. So I love talking to people, to kids, about my passion for space, why space is so cool. There's so much stuff out there to discover. And so I sort of have a little bit of a unique background where I have the sort of like scientific form, like training to be an astrophysicist, but I also have a lot of experience doing education and communication. So that's why I was like a really good fit for the outreach scientist for this mission.
Excellent. And of course, you are physically embodying the James Webb Telescope here. I assume this was for Halloween?
Yes, that's right. This is for Halloween. So of course, the Webb telescope was one of my inspirations for this, but actually another inspiration, my partner for the last 15 or so years dresses up as a household item with a big cardboard box costume he makes. So I told myself I should make a cardboard box costume of Webb. I gave myself a challenge. It took a few days, and I gave out candy dressed up as the Webb telescope, and kids recognized me. So I love doing outreach while thinking outside the box, and this is an example of that.
Well, speaking of giving out candy, James Webb certainly gave us some eye candy on Tuesday. So why don't we get into some of these amazing images that were released just a few days ago?
Yeah, absolutely. So the first image that I'm going to show, this one right here, is the one that was actually revealed on Monday. So the White House was so excited. They wanted in on the reveal. So President Joe Biden, Vice President Kamala Harris, they were briefed by some of my colleagues from NASA, and they revealed from the White House this first image of a galaxy cluster. So in this image alone, which represents the size on the sky that's equivalent to 1 grain of sand on the tip of your finger held at arm's length, that is how big this patch of sky is in our sky. And there's 7,000 galaxies in that little dot alone. Gosh. And that tells you, number one, it tells you that the universe is really filled with galaxies, filled to the brim. And number two, it shows you the amazing resolution the telescope has. From that grain of sand, it can discern 7,000 individual galaxies. That is absolutely mind-blowing.
Yeah, and I think what's interesting, because I was a very big fan of the original deep field images that were taken by the Hubble Space Telescope. So what's the big difference here with the deep field that JWST was able to get?
Yeah, so one of the really key differences, and this was actually the reason why Webb was set into motion in the 90s as a successor to Hubble. We knew that Hubble was going to look very far in the universe, but because of something tricky called redshift, which is caused by the expansion of the universe, the very first galaxies who were brightly emitting right after the Big Bang, they were shining in blue light, in visible light, in ultraviolet light even. But because as the light traveled through an expanding universe, that light got stretched out into red colors or infrared light, which is invisible to us and invisible to Hubble as well. So in
Wow.
order to spot those very first galaxies, we needed to build an infrared telescope, which is the case with Webb. So here we can see these very distant galaxies that are bright in the infrared that Hubble couldn't see. So on top of the resolution, we're getting more distant galaxies that can only be seen in the red.
Yeah, you can certainly see sort of like smattering around the outside of this photograph, lots of those red galaxies, which would be the shifted galaxies that are very far away, just as you described. And I'm also seeing a little bit of those Einstein curves of the warping of the light, which I have heard potentially could be one galaxy, could be a couple. Do you have any information on what the nature of those galaxies are?
Yeah, absolutely. So I'll just highlight them right there. You can see there's a curve there, there's a curve there. People are loving this galaxy here, which is also curved. And this is caused by a phenomenon called gravitational lensing. So when we're saying that this is a picture of a galaxy cluster, a big group of galaxies, that's only half of the truth because as we know, we live in a 3D universe, but we are taking 2D pictures. So this 3D projection of all these different galaxies are smushed down into one image. So we do have a galaxy cluster that's about 4 billion light years away in the foreground, but in the background, we have much more distant galaxies that are 10, 12, 13 billion light years away. And as their light travels through space towards us, the light of these galaxies is actually warped, deformed around the deformation caused by the mass of the galaxy cluster that's in between us. So these curves are actually those distant galaxies behind the cluster, but their images are oddly shaped because of the warping of the very tissue of the universe caused by the gravity of the galaxy cluster. And we can actually tell with the Canadian instrument, we took a special measurement called a spectrum of this weird galaxy here and this weird galaxy here. We compared them to each other and they were identical. It's sort of like we fingerprinted the galaxies with the Canadian instrument. The fingerprints came out identical, which means that they're actually the same galaxies. They're a single galaxy whose image has been doubled, caused by the gravitational warping of the big mass of the galaxy cluster in between. And that was a discovery done because of the Canadian instruments.
Wow, just incredible. I'm having to shift around my dome here because the sun keeps shining on my screen, but these images are just incredible. So this was the sneak preview image that, of course, the White House needed to get in on before the big release day. I guess they have veto power. They can get in there because it certainly seemed like NASA was holding down these images quite tightly. Like there was no leaks that were happening for this release.
No, I got to see them early because I was part of the broadcast. And so we needed some time to digest, but only a handful of people got to see them before this week. So I got to see them last week and I was maybe one of maybe 100 people in the world who got to see them early.
Okay, so I assume that you were not tempted to tell anyone about these images. You were true to
Of
your
course.
your astronomer oath. Let's move on to the next image that was released, which was yes, this was the image that you were supposed to describe. And of course, I find really interesting that this image, which was taken with the NIRAS, is that how you pronounce it?
Nearest.
NIRAS. It's an acronym. I guess there's no right or wrong way. But it is the Canadian instrument, which is why in the feed, NASA went to the Canadian Space Agency and you as the outreach scientist to describe this image, which is less of an image and more of a data set. So on the surface may seem less vibrant, but actually is perhaps the coolest image and the most important image of the five. Tell us about what we're looking at here.
Yeah, and I did see that sentiment expressed. A lot of people were saying, don't worry, we still love the spectrum. I'm most excited about it, even though it's not as visually striking. So here you can see something that's called a transmission spectrum. And this is essentially telling us the composition of the atmosphere around an exoplanet called WASP 96b. So this exoplanet is about 1,150 light years away. So quite far away, but within our own galaxy. And it's what we call a hot gas giant or a hot Jupiter. So it's very large and puffy and big like Jupiter, but it's actually very close to its star. It only takes 3 days for it to go around the star. So it's very hot, 500 degrees Celsius there. And we can do something very clever when the planet passes in front of its star called transit spectroscopy. So when a planet passes in front of its star, that's called a transit. And when that happens, the brightness of the star goes down momentarily. This is called a light curve. And this is the light curve for this planet that was collected by the Canadian Nearest instrument on Webb. So you can see the starlight is flat, and then when the planet passes in front, the brightness of the star goes down a little bit and then goes back up right there. But while this is happening, if the planet has an atmosphere, some of that starlight streams through the atmosphere and is again fingerprinted with the chemicals found inside the atmosphere of the exoplanet. And so these bumps and wiggles are that fingerprint. And from that fingerprint, we can tell that we've detected water vapor and clouds and haze inside of the atmosphere of this exoplanet.
This is amazing. So in picking a planet, you must have had like a lot of options to choose from of all the exoplanets that have been discovered so far. Why did you pick WASP 96b?
Yeah, so WASP 96b is a planet that was previously observed with the Hubble Space Telescope. And so this water detection is not actually new. It's a confirmation that we are doing of a previous discovery with Hubble. We wanted to give Webb, we wanted to push the envelope, but we still wanted to give it reasonable targets, things to confirm for its first images. So we picked something that we already knew a little bit. And because it's a big planet, it's easier to study. Smaller planets are harder, but so interesting. So we're going to do them very, very shortly. But one thing that's super interesting with the Hubble data, we saw no evidence of clouds or haze, which we thought was very odd. We usually, gas giant planets like Jupiter or Saturn are filled with clouds, but we thought, okay, I guess this planet is weird. But with the better Webb data, we now do see evidence of clouds and haze. So even with this very first data set, we are rewriting what we know about this planet based on previous data.
Oh, this is super exciting. So I assume, as you've just said, there's going to be more data to come out. I assume, already picked a few more planet candidates that maybe have already been looked at. And what's next for this particular instrument on James Webb?
Yeah, absolutely. So super exciting. The first year of observations for Webb have already been scheduled. And one of the first targets that's actually being led by a Canadian, one of my colleagues at the University of Montreal, she's a PhD student, Olivia Lim, and she's leading the largest Canadian program on Webb this year. She's going to be looking at planets in the TRAPPIST-1 system, a super exciting system, 7 rocky exoplanets, three of which are in the habitable zone, so might have liquid water. And so very interesting targets to look for habitable worlds.
Okay, that is super exciting. Looking forward to hear about that. So for our last 10 minutes, Nathalie, why don't we quickly look at some of the other images that came out. This beautiful one here, this was a nebula, I believe.
Yes, that's right. So we've talked about galaxies, we've talked about exoplanets, but another key goal for Webb is to study the life cycle of stars. So stars are kind of like humans. They are born, they live, and then they die. And so this is a stellar nursery or a star-forming region in a nebula called the Carina Nebula, which has been imaged in the past by Hubble, but really, really beautiful. And you can see right here, this is a comparison between what we saw with Hubble up top and what we see with Webb below. And one of the wonderful things with infrared astronomy, infrared light, is that it actually pierces through cosmic dust. And we know stellar nurseries are very, very dusty places because the stars are feeding on the dust, they're blowing out dust as well. And so all of these dark regions, that is dust that's blocking out starlight. But by looking at the infrared, you can see through that star, that dust, and look at all of these little stars being born within the stellar nursery, and all of this texture in what we're calling the cosmic cliffs of the Carina Nebula. So we can already see so much more detail than what we had with Hubble in this picture.
Yeah, it's just such a striking image, and of course, it's hard not to compare it to a beautiful mountain range because it does look, as if we're looking above a starry night on a beautiful mountain range, maybe not unlike the Rocky Mountains we have here on the West Coast, and you can really see the difference between the two images. Certainly, I've been fielding lots of questions about like the differences. Certainly the reason they chose some of these iconic photos that Hubble had already taken is that so we could do this kind of comparison, right?
Yeah, exactly. So, and I always want to emphasize this, we still love Hubble. Hubble has been doing wonderful work for 32 years and is still growing strong. And the two observatories are very complementary. Hubble can look at visible light and can make great discoveries, and then Webb can make great discoveries in the infrared. They can work in tandem together. But we have to remember what the first images from Hubble looked like. Hubble had a rough start. It had problems with its mirrors. It needed to be fixed 3 years down the line. When you think of the fact that the Webb images were only taken over the course of 5 days, were analyzed and reduced very quickly. This is the very first display. We haven't even tried that hard yet. It's amazing what to think is coming up next with Webb.
Right. It sounds a bit like perhaps in a sporting event, you got the superstar and he's coming in. You got the veteran on the team. Hubble's the vet. You got the new hot young rookie here, and JWST is just getting warmed up.
That's right.
Lots to come from this hot new rookie here. Let's look at some other of these images from JWST. This amazing one of a dying star.
Yeah, that's right. So we were just talking about the life cycle of stars, and we have a beautiful image of a stellar nursery, but this is an image of a stellar death, the death of a star that is very similar to our own sun. So we think about 97% of stars will die and become a planetary nebula, which is what this is called. This is the Southern Ring, a planetary nebula. And at the end of a typical star's lifetime, it will puff up into what we call a red giant and then eject successive layers of its envelope. And all of the structure that you see, lines like this, those are those successive layers of envelope that is being blown off. And at the very center, you have the corpse or the cadaver of the star that's left. And you might think it is this star here, but it is not, because we know at the heart of this planetary nebula, there are actually two stars. It is a binary system that is interlocked together. And the one that actually caused the planetary nebula is only visible, or very much more visible, in the right picture, because this was taken in the mid-infrared by another one of Webb's instruments, NIRI. This one is in the near infrared by NIRCam. So the dead star is actually this red one right here, because it is so enshrouded in the dust that it has blown off. It needs mid-infrared observations in order to become visible, because the dust itself is shining in the mid-infrared. This one, the very bright blue one, is still alive, but we think eventually it will blow off its own planetary nebula, and you'll have this sort of double nebula going on.
Oh, this is so amazing. I've never really seen a comparison like this with two different infrared images, and just showing like how different, even in the infrared spectrum, within the infrared spectrum, there is a spectrum within that to show you some very fine details, including, as you just said, that binary star system, which you don't see on the image on the left.
Yeah, absolutely. So in the near infrared, that's very, very useful for looking through that dust and seeing what's hidden behind it. But the mid infrared is actually what dust and gas itself shines in. And often as astronomers, we find gas and dust very, very bothersome because it's hiding what we're actually trying to look at. But it's actually so important because it's what forms stars and forms planets. So in order to understand how planets and stars form, we need to understand the sort of like the Lego pieces, the constituent pieces. So the mid-infrared is essential for understanding the dust itself.
Right. Got a question from Clive, who's wondering if you have any preference for any previously beautiful pictures that Hubble's taken that you'd like to see J. Davis T take a close look at.
So one of my favorite pictures that Hubble took was of the antennae galaxies, and it's actually related to this picture that was taken by Webb. It's two spiral galaxies that are in mid-collision, and I love it so much. It's like the background on my phone and everything. And because with the Hubble picture, you can see these like bright pink fireworks going off in the galaxies where new stars are being formed, where gas is being compressed. And I would love to see the antennae galaxies with Webb, but in the meantime, to keep me waiting, I have Stephan's quintet, which is a group of 5 galaxies, 4 of which are interacting and 2 of which are crashing into each other. So this is a really good teaser.
Yeah, and I found it really funny on the NASA webpage. They even shout out that Stephan's quintet got his first starring role in the movie It's a Wonderful Life, which I was like, wait a minute, what? So I had to rewatch the scene. I was like, oh, it's so fascinating to see what the images we had of Stephan's quintet, which were taken with normal ground-based telescopes, just 4 kind of blobs, and now we see it in a whole new, very detailed light.
Yeah, absolutely. And one thing that I love about this picture, this is a combination of near infrared and mid infrared picture. But if you take away the near infrared, you only look at the mid infrared. Here again, what is mostly shining through is the gas and the dust. You're taking away a lot of the stars. So you're almost seeing like the gas skeleton of the galaxies here rather than like the entire thing. And a little hidden surprise that you can see in the top galaxy right here, there's a very bright spot at the center, and that is a supermassive black hole, once again enshrouded in gas and dust, which it's actively feeding on. And we've been able to take spectroscopic measurements of that active galactic nucleus, that supermassive black hole, and we know that the dust around it is sort of like beachy sand, but a little bit finer than that. It's like silicates. We were able to determine that, and we can even calculate the speed at which the jets coming out of the supermassive black hole are going. So already so much information in these pictures.
Just incredible. That this is just blowing me away. Such an exciting week for space. Just wrapping up the show here, Natalie, got one last question from Pride to go back to the exoplanets. Are we going to be able to see any close-up images of exoplanets?
So that's a very good question. And you might have seen in the background of the spectrum, you have this sort of hazy image that is just an artistic representation. It is incredibly hard to take real pictures of even our own planets in our solar system. We have to send probes over there to get those pictures. It is, however, possible to take real images of exoplanets, but they only look like bright dots. And it only works for certain types of exoplanets that are bigger, puffier, brighter, and far away from their stars. But there is a special mode on the nearest Canadian instrument, which allows you to take real pictures of exoplanets. But we're a very long way away from being able to see clouds and dust and landscapes on these worlds, unfortunately.
Right, right. So this is actually giving us a more detailed, quote unquote, picture of understanding, maybe not a visual picture of the
That's
exoplanet.
right.
But speaking of
Exactly.
planets in our own solar system, we are going to be getting some pictures of some of the planets in our solar system pretty soon with the JWST, right?
Yeah, exactly. So we can look at the solar system, anything from the orbit of Mars and beyond. We can't look at the sun, Mercury, Venus, the Earth, or the moon, because if we pointed the telescope towards the sun, it would fry everything. We need to keep the telescope super cold. That's why we have a sun shield there. So we have really exciting programs set up to look at Uranus, Neptune, and a lot of the moons around the planets Jupiter and Saturn as well.
That's going to be super. We're looking forward to that. Nathalie, thank you so much for joining us. Giving you I know it's not as big as a NASA a worldwide feed, but very glad that you're able to join us here on Ask an Astronomer. I'm hoping we can join and listen to you and the many discoveries, I'm hoping.
Yeah, definitely. I'm still sticking around on the mission, and the science is only getting started now. So there's going to be so many discoveries in the next weeks, months, and we hope the mission will last upwards of 20 years.
And just like the NASA feed, my internet connection is a little bit unstable, but I think we're going to blame it on Rogers. Okay, Rogers is doing us a dirty here. But thank you all so much for joining us here on YouTube and on Telus Optic. We will be back live. Marley will be back in a couple of weeks. In 2 weeks, Thursday, 2 p.m. Pacific time. We will see you all then. Take care, everyone.
See ya.